How does energy travel across the vastness of the entire universe, or, even just across a crowded room, without actually moving a single atom of mass from point A to point B? Seriously, think about that for a second. It's a phenomenon so incredibly common that we take it completely for granted, yet the mechanics behind it, they will absolutely change how you look at the physical world.
Welcome to today's Explainer. We're going to explore the absolute core concepts of Class 11 physics by following the fascinating journey of a wave. And honestly, once you really understand how waves operate, you start seeing the underlying rhythm of literally everything. We're talking the music you listen to, the light entering your eyes, even the very structure of the cosmos itself.
Okay, so here's our game plan for today. We'll start with the anatomy of a wave, move into decoding the wave equation, look at the principle of superposition, explore reflection and standing waves, and wrap up with beats and the Doppler effect.
All right, let's dive into Section 1, Anatomy of a Wave, the core of the disturbance. Before we can do any of the math, we really need to understand what a wave actually is at its most fundamental physical level. And the absolutely crucial point here is this: waves transfer energy, not mass. This is basically the biggest misconception out there. To wrap your head around this, just imagine a ball drifting a few yards out at sea. As a massive wave rolls in towards the shore, that ball doesn't travel to the beach with the wave, right? It just bobs up and down. The disturbance, the actual energy, moves forward, but the water itself and the ball resting on it, they just oscillate right there in place.
And that bobbing motion perfectly illustrates the two main ways this oscillation can actually happen. First, you've got transverse waves. This is like flicking a heavy rope or how light travels through space. The particles oscillate perpendicular to the direction the energy is moving. So they create these distinct high points, which we call crests, and low points, called troughs. Then, on the other hand, you have longitudinal waves. Sound is the perfect example of this. In this case, the particles oscillate parallel to the wave's travel. So instead of up and down, they create areas where the medium gets all bunched up. Those are compressions, and areas where it spreads out, which are called rarefactions. To actually measure these beautiful physical shapes, we rely on three foundational definitions. First up is wavelength, denoted by the Greek letter lambda. This is simply the physical distance between two subsequent crests, or two troughs. Second is amplitude. This is the maximum height or displacement of the wave from its resting position. You can basically think of this as the wave's strength. And third is frequency, which is just how many of these crests pass a specific spot in a given amount of time. Get these three terms locked in because they form the foundational vocabulary for the rest of our journey.
Moving right along to Section 2, Decoding the Wave Equation, Math in Motion.
Now that we have our physical shapes and definitions sorted, it's time to translate that vibrant movement into some elegant mathematics. The brilliant scientist D'Alembert realized something really profound about wave shapes. He noted that a wave's shape propagates at a constant velocity without ever changing its fundamental form. Mathematically speaking, if you have a shape defined by a position x and it's moving at a velocity v over time t, you can track that entire moving shape using the simple argument x minus vt. It's a remarkably simple yet incredibly powerful framework.
So, we can actually take D'Alembert's concept and write out the harmonic progressive wave equation. It sounds complex, but it's simply tracking a single disturbance across space and time. In the equation, y is the displacement of a particle. A is our amplitude. Then inside the sine function, kx relates to our spatial position and our wavelength, omega t relates to time and frequency, and phi is our initial starting phase. When you plug real numbers into this equation, you are essentially drawing the wave frame by frame as it travels. But translating physical reality into math isn't always perfect on the very first try. Take the speed of sound in a gas, for example. Sir Isaac Newton originally calculated this, assuming that as a sound wave creates all those compressions and rarefactions, the temperature of the air stays constant. He thought it was an isothermal process, but his result? It was totally inaccurate compared to real-world measurements. Later on, Laplace came in and made a vital correction. He realized that sound waves move so incredibly fast that heat literally doesn't have time to flow out of the compressions. It's an adiabatic process. By adding the adiabatic index, gamma, Laplace's correction perfectly matched physical reality. It's just a great reminder of how science constantly self-corrects to find the truth.
Section 3, The Principle of Superposition, When Waves Collide.
So far, we've only looked at a single wave traveling all by itself. But let's be real, the universe is messy. What actually happens when two separate waves intermix in the exact same space? Well, waves don't just crash into each other like cars do. They interfere with one another. But for this interference to be clean and measurable, there are three strict conditions that must be met.
First, the two waves need the exact same frequency and roughly the same amplitude. Second, they've got to be moving in the same direction. And third, they need a constant phase difference, meaning they have to stay perfectly in sync with one another over time.
When these waves occupy the same medium at the same time, we apply the core rule of superposition. The resultant displacement of any particle in that medium is simply the vector sum of the displacements caused by the individual waves. What does that mean in plain English? You basically just add their forces together at any given instant. If wave A pulls a particle up by 2 units and wave B pulls it up by 3 units, boom, the particle moves up 5 units. It's just beautiful, simple addition.
Now, what's really fascinating is the dramatic real-world difference this addition actually creates. When the crests of two waves perfectly align, you get constructive interference. Their amplitudes add up, creating a massive spike in intensity, meaning you get a much louder sound or a much brighter light. But on the flip side, you have destructive interference. If the crest of one wave perfectly aligns with the trough of another, they essentially add up to zero. They completely cancel each other out, which literally results in total silence or pitch darkness. It's wild to think about.
All right, Section 4, reflection and standing waves, trapping the energy. So what happens when our traveling disturbance doesn't hit another wave, but instead slams into a physical boundary and bounces back? Well, the way a wave reflects depends entirely on what it hits. Take a rigid boundary, for instance, like a string tied tightly to a solid brick wall. The reflected pulse is inverted. A crest bounces back as a trough, its phase is completely reversed. Now compare that to a free boundary, like a ring sliding freely up and down a pole. In that case, the reflected pulse remains upright. A crest bounces back as a crest, with absolutely no phase change at all.
So, imagine you are continuously sending waves down a string, and they are continuously reflecting right back at you. You now have two identical waves traveling in opposite directions in the exact same medium. According to that principle of superposition we just learned, they are going to intermix. And when they do this perfectly, they form what is called a standing wave. It's an illusion where the wave appears to stand completely still, basically trapping the energy in localized spaces rather than traveling forward.
To read a standing wave, you really only need to look for two specific features. First are the nodes. These are the specific points in the medium that stay completely at rest all the time. This is where destructive interference is permanently happening. Then you have the antinodes, which are the points right between the nodes. The medium here experiences maximum displacement and energy. This is where constructive interference is at its absolute peak. And by the way, understanding nodes and antinodes, it is the absolute secret key to understanding how every single musical instrument in the world works, from the string of a classical violin to the air vibrating inside a massive organ pipe.
Finally, Section 5, beats and the Doppler effect, sound in the real world. Let's step out of the abstract math for a second and look at how our human ears actually perceive all these complex wave interactions in everyday life. Have you ever heard two slightly out-of-tune instruments play the same note, and you notice this strange pulsing wub-wub-wub sound? That auditory pulsing effect is called a beat. It happens when two waves have incredibly close but not perfectly matching frequencies. Because their frequencies are slightly off, they constantly drift in and out of phase with each other. They alternate between constructive interference, which sounds loud, and destructive interference, which sounds soft. This creates a really distinct periodic waxing and waning of the sound intensity.
The speed of that pulsing is what we call the beat frequency. For example, let's say you have two sitar strings playing a note, but they're just slightly out of tune, producing a pulsing beat frequency of 3 Hz. That means you literally hear 3 distinct volume swells every single second. A trained musician knows they can tune the instrument by tightening the tension of one string, bringing its frequency closer to the other. They'll hear that 3 Hz beat slow down to 2, then 1, and eventually it completely disappears when the strings are finally in perfect sync.
Another incredibly common real-world wave phenomenon is the Doppler effect. We define this as the apparent change in frequency or pitch due to the relative motion of a sound source and an observer. Come on, we all know this sound. It's the classic sound of an ambulance speeding past you on the street. The siren sounds high-pitched as it approaches, and then it instantly drops to a lower pitch as it drives away. Here is how we actually track that mathematically. When the source moves toward the observer, the sound waves get physically bunched up in front of it. This decreases the wavelength and increases the apparent frequency, which results in that higher pitch. But when the source moves away, the waves get stretched out behind it, decreasing the apparent frequency for a lower pitch. When you are calculating this on paper, the golden rule to remember is that velocity is always considered positive in the direction from the source to the observer. If you follow that specific sign convention, your math will always perfectly match what your ears are hearing in reality. And that, my friends, brings our journey to a close. We've taken some pretty dry mathematical equations and seen exactly how they dictate the beautiful, highly energetic reality of our physical universe. So, the next time you hear an ambulance siren wailing down the street, or you pluck a guitar string, or even just watch the ripples in a puddle after it rains, take a second to ask yourself, what invisible waves are crashing, reflecting, and superimposing around you right at this very moment? Keep observing, keep questioning everything, and I'll catch you in the next explainer.